Good morning, children. Uh, welcome to the physics class, and we will start today's topic with electrostatics. This is the first lesson in your physics textbook, volume 1. Now, as the name implies, electrostatics, it is the branch of electricity which deals with stationary charges, and it is called as electrostatics because statics means stationary. Now, in order to understand electrostatics, we'll have to see something about electromagnetism, which we will see in the next slide. So in this slide we have electromagnetism, that is, you have a nail, an electromagnet, a cell which converts electric to magnetism, or you can say both of them are interrelated, because electromagnetism is one of the most important branches of physics which deals or you can say the technological developments of the modern 21st century are primarily due to the understanding of electromagnetism. Now, if you remember in our 11th standard, we studied about the nature of forces, or the four types of forces. In that, we had gravitational force, tension force, frictional force, and the normal force. Now, what Newton said was each of these forces are independent of each other, and he also said they were separate natural forces. Now, if you see in our day to day life, we experience all these types of forces in our daily activities. We will see some examples of it. See, in this slide, we see a man pushing a car. Now, what happens here is when the object, that is a car, is pushed, the atoms in our hand interact with the atoms in the object, and this interaction is basically electromagnetic in nature. So, this you call it as an electromagnetic force. In this slide, you see the person with the apple. So naturally, we will term it as your gravitational force, because as soon as we see an apple, we say it is Newton, and it is going to be your gravitational force. Now here, when we stand on the Earth's surface, the gravitational force acts on us, and it acts downwards, and the normal force acts in the upward direction to counterbalance this gravitational force. Okay. Now, what is the origin of this normal force which is acting in the upward direction? Now, this also arises due to electromagnetic interaction between the atoms on the surface of the earth and the atoms present in the feet of a person. Though we are attracted by the gravitational force of the earth, we stand on earth only because of electromagnetic force of atoms. Now, in the next slide, you see a person climbing on a mountain. Now, here static and kinetic friction comes into play. When the object is moved on the surface, that is, a man is considered as an object. When he is moved on the surface, static friction resists the motion of the object. Now, this static friction arises due to electromagnetic interaction between the atoms present in the object and the atoms on the surface. In the similar way, you can explain kinetic friction also. So, from these examples, it is very clear that understanding electromagnetism is very, very much essential to understand everything which is taking place in the universe. We'll be dealing with electromagnetism, or the basic principles of electromagnetism, in a separate chapter in volume 1. Now, in this slide, you see two materials, that is amber and ebonite. What are these amber and ebonite? Now, if you see, Greeks around 2 millennium years ago, they found what you call as amber. It is basically a solid which is a translucent material which is formed from the resin of a fossiled tree. Okay. Now, when they took this amber and they rubbed with animal fur, it started to attract pieces of leaves and dust. So they said that amber is having a special property which can attract charges. So they said it was charged. Later on, they found out that many other materials also possess this property. For example, ebonite, or when a glass rod is rubbed with a silk cloth, it attracts pieces of paper, or ebonite rod rubbed with fur, it attracted or it produces charges. Now, you have here a rubber rod, and now Now from this rubber rod, we can explain what is attraction and repulsion. You have a glass rod and a rubber rod. Okay. Now if you see, if you just hang a rubber rod using a thread, okay, and you bring another rubber rod near it, the rods repel each other. Now, if you bring a charged glass rod close to it, close to the charged rubber rod, then they start to attract. So, we can conclude that similar charged particles will repel at each other, and different charged particles will attract each other. Now, what are these charged particles? As I told you, you can produce charges by many ways. One is by attraction, by rubbing. You call it as rubbing. So, when a glass rod is rubbed with a silk cloth, it produces positively charged particles, and when an ebonite rod is rubbed with fur, it produces negatively charged particles. So, like charges will repel each other, and unlike charges will attract each other. Now, Benjamin Franklin, he suggested there are two kinds of charges which existing in the universe, and this he found out in the 18th century. So he called one type of charge as positive charge and the other one as a negative charge. And based on Franklin's convention, rubber and amber rods are negatively charged, while glass rod is positively charged. So the final conclusion was like charges repel each other and unlike charges attract each other. Next we have J.J. Thomson and Rutherford. Now what they did was, they did many works or experiments in this field, and in the late 19th century and in the beginning of the 20th century, they came to understand that the atom is electrically neutral and it is made up of negatively charged electrons, positively charged protons, and neutrons which have zero charge. So, all the materials will have these types of charges. Next, we talk about triboelectric charging. What is this triboelectric charging? Now, the charging the objects through rubbing is called as triboelectric charging. Now, having known about charges, that there are two types of charges, positively charged particles and negatively charged particles. Now, we will see the properties of charges. Now, if you see the properties of charges, you have first one is electric charge, next one is your conservation of charges, and the third one is quantization of charges. The first one, electric charges. Objects in the universe are made up of atoms which are made up of protons, neutrons, and electrons. And if you see, electric charge is a fundamental property of particles. So every particle will produce a charge. And if you see the SI unit of charge, it is coulomb. Next, you have the conservation of charges. Benjamin Franklin argued that when one object is rubbed with another object, charges get transferred from one to the other. For example, when a glass rod is rubbed with the silk cloth, some negative charges are transferred from glass to silk. As a result, the glass rod is positively charged and the silk cloth becomes negatively charged. From these observations, he concluded that charges can neither be created nor be destroyed, but can only be transformed from one object to another. So he called it as conservation of total charges. So the total electric charge in the universe is constant, and charge can neither be created nor be destroyed. In any physical process, the net change in charge will always be zero. Next, we come to the third property, that is the quantization of charges. What is the smallest amount of charge that can be found in nature? Now, experiments show that the charge on an electron is minus E and the charge on the proton is plus E. E denotes the fundamental unit of charge. Say suppose charge Q is equal to an integral multiple of fundamental unit of charge E. So we call it as Q is equal to N into E, where N is an integer, 0 or plus or minus 1, plus or minus 2, and so on it goes on. And this is known as quantization of charge. Suppose say when a glass rod is rubbed with a silk cloth, the number of charges transferred is usually very large, of the order of 10 to the power of 10. So you call it as the macroscopic level. Hence the charges are treated to be continuous. But at the microscopic level, quantization of charge plays a vital role. In the next slide, we will see the value of the charge. E is equal to 1.6 into 10 to the power of minus 19 coulombs. The charge of an electron is minus 1.6 into 10 to the power of minus 19 coulomb, and the charge of a proton is plus 1.6 into 10 to the power of minus 19 coulomb. At the microscopic level, quantization of charge plays a vital role. Next we have Coulomb's law. This is Coulomb. In the year 1786, he deduced the expression for the force between two stationary point charges in vacuum or free space. So he considered 2 point charges Q1 and Q2, which are at rest in vacuum and are separated by a distance r. Now according to Coulomb, the force on the point charge Q2 exerted by another point charge Q1 is given as F21, which is equal to 1 by 4 pi epsilon naught Q1 Q2 by r squared, where that 1 by 4 pi epsilon naught is a constant and it is represented as K. This is the diagrammatic representation of Coulomb force between 2 point charges. So you have 2 point charges Q1 and Q2 separated by a distance of r. The force that is acting is represented as F21, which is nothing but the force exerted by the second body on the first body. The next slide shows us the important aspects of Coulomb's law. The first one says electrostatic force is directly proportional to the product of the charges and inversely proportional to the square of the distance between the 2 point charges. I repeat, electrostatic force is directly proportional to the product of the charges, that is Q1 and Q2, and inversely proportional to the square of the distance between the 2 point charges, that is r. The second aspect is the force on the charge Q2 exerted by the charge Q1 always lies along the line joining the two charges. The third aspect is, as I told you, F is equal to K into Q1 Q2 by R squared, we said, where K is a constant. The value of K is equal to 1 by 4 pi epsilon naught, where epsilon naught is known as the permittivity of free space, and the value of 1 by 4 pi epsilon naught is equal to 9 into 10 to the power of 9 Newton meter squared per Coulomb squared. This value you should note because when you're working out problems, you can just substitute 1 by 4 pi epsilon naught as 9 into 10 to the power of 9. Okay, and the value of epsilon naught is equal to, that is the permittivity of free space, the value of that is equal to 8.85 into 10 power minus 12 Coulomb squared per Newton per meter squared. The value of epsilon naught may come as a 1 mark question. Then the fourth aspect is the magnitude of the electrostatic force between two charges, each of 1 coulomb, that is when Q1 and Q2 is equal to 1 coulomb and the distance r is equal to 1 meter, then F will be equal to 9 into 10 power 9 into 1 by 1 square, that is 9 into 10 to the power of 9 newtons. So this is a huge quantity, almost equivalent to the weight of 1 million ton. So we never come across 1 coulomb of charge in practice. So most of the electrical phenomena in day-to-day life involve electrical charges of the order of microcoulomb or nanocoulomb. And the fifth point says in SI units, Coulomb's law in vacuum takes the form as 1 by 4 pi epsilon naught Q1 Q2 by R squared. In medium, in a medium of permittivity epsilon, the force between 2 point charges is given as, instead of epsilon naught, we'll have to write it as epsilon. That is 1 by 4 pi epsilon Q1 Q2 by R squared. Now, since epsilon is greater than epsilon naught, the force between 2 point charges in a medium other than vacuum is always less than that in vacuum. So, we define the relative permittivity for a given medium as epsilon r. Epsilon r is the relative permittivity and it is given as epsilon by epsilon naught. So, for vacuum or air, epsilon r is equal to 1, and for all other media, epsilon r is greater than 1. And the next point, it says both, that is both means Coulomb's and Newton's law of Coulomb's electrostatic law and Newton's gravitational law. Both are inversely proportional to the square of the distance between the particles, and electrostatic force is directly proportional to the product of the 2 point charges, whereas gravitational force is directly proportional to the product of the two masses. Okay. Then we see the difference between Coulomb and Newton's law of Coulomb's electrostatic force and Newton's gravitational law. See, the first one is, it is all gravitational force, it is always attractive between two masses, whereas Coulomb force, it can be attractive or repulsive depending upon the nature of the charges. And in gravitational force, capital G is equal to 6.626 into 10 to the power of minus 11 Newton meter squared per kg squared, whereas in Coulomb force, K is equal to 9 into 10 power 9 Newton meter squared per Coulomb squared. Gravitational force, it is independent of the medium, whereas Coulomb force, it depends on the nature of the medium in which the two charges are kept at rest. And the last point, gravitational force, it is the same whether 2 point masses are at rest or in motion, whereas Coulomb force, if the charges are in motion, yet another force, we call it as a Lorentz force, comes into play in addition to Coulomb's force. I think you have understood the presentation, children. So go through the presentation again and again, and at the end, that is, I will be releasing this video at around 3 o'clock, and at most probably 4:30 I will give you a 1 mark test. That is, I will post a question, around 10 question answers, just one word questions, which you should answer immediately within 30 minutes and post it. Okay. Let's see how you people answer. All the best. Thank you.